So you feel better about the light-dependent reactions? Like that's more quizable now? Maybe you'd answer more questions right about it than you would have before yesterday. So quick overview again, that we have the light-dependent reactions, which take water and the ADP plus P and NADP plus and create oxygen as a byproduct, but more importantly, ATP and NADPH to power the light-independent reactions, which take carbon dioxide from the air, pull it apart, rearrange it, play Legos with it, and turn it into glucose. Then the used up ATP and NADPH goes back to get re-energized in the light-dependent reactions. We're good with that. Any questions? I think you guys are pretty solid. We went through a couple of times the light-dependent reactions. One more time. It's light exciting an electron, the electron dumping down electron transport chain. Water furnishing the replacement electrons to chlorophyll, and also oxygen as a byproduct given into the atmosphere, and protons that will join the other protons in the thylakoid. The excited electron jumps down the chain, in the process pumping a bunch of protons into the thylakoid. That electron, now exhausted, gets re-excited by light and handed off to NADP+, creating NADPH. The buildup of protons that electron and many others has caused is the mechanism by which ATP gets made by the ATP synthase. The ATP synthase, kind of like a water wheel, it's the force of escaping protons that spins it, and when it spins, it makes ADP and P into ATP. Lauren?
Why is that one disk in the electron transport chain longer than the others?
Because that's kind of what it looks like physically. It's almost like across textbooks, when you see something kind of like this with a couple of, and they're often squared off, but a couple of short ones and a long one and then a short one, that's kind of how they draw electron transport chains, because there's more than one. You'll see them other places. Other questions?
So what does the electron lose or gain when it goes through the little transport?
It loses energy step by step, and that energy is converted into the energy that pushes protons this way. Yeah, good question.
So the only reason it has to go from order system 2 to 1 is to make sure that protons are on that side?
Yeah, so the job it's doing when it goes between the two photosystems is it is very much directly causing those protons to move in. Yep. And then the second job it has when it gets re-energized is to form NADPH. Yep. Good? We ready? Now, this is the one that like you're really knowing details of. We're going to go a little broader on the Calvin cycle, on the light independent reactions. What you're gonna draw is pretty simple. I'll show you the complicated version, and then I'll tell you the fairly basic things you need to know about. By the way, tomorrow you are going to get a piece of paper that has both light dependent and independent on either side, just so you have it. I'll give you the slide as well, so you can step through it if you want. Okay, so just for the sake of your flashcards, let's write down reactants and products, which is what goes in and what comes out of the light-dependent reaction. And you could probably just come up with these on your own, right? What are the reactants? What goes in to the light-dependent reaction?
NADP plus.
Okay.
ATP plus phosphate, water.
ADP plus phosphate, right?
Yeah.
Low energy form.
Yeah, and then water and light.
We don't count light because it's not a physical part, like it's not an actual reactant, but you're right. Yeah, so water, ADP plus P, and ADP plus, the low energy forms. Product?
Air, ATP, and
ATP, NADPH. What was the other thing? O2. Good. Not just air. Air is all the gases, right? This is just a particular one. ATP, NADPH, and oxygen gas. And you really don't have to know much about the details of either of these reactions to get reactants and products. You basically just need that overview diagram that you drew. Light independent reactions. If you know that diagram, you already know. What goes in? Well, two of them you know cold, right? The two that go back and forth and back and forth and back and forth. What are they? What's going to go into the light independent reactions?
An ADPH.
Yeah, the high energy versions of those two molecules are reactants. What's the third reactant that goes in? The raw material that you need. Will? Absolutely. Yeah. Smarter than a Harvard graduate. Okay, what comes out? Glucose, most importantly. And then the recycled versions of those high energy molecules, right? Glucose, ADP plus P, and NADP plus. Flashcards, and the purposes of any test questions that show up that say, what are the products or what are the reactants of blah? That's really, that overview diagram gives you that. That's what that's for. Is you can track all those things and figure out what's reactants and what products. And that overview diagram will also tell you where those reactants came from and where those products are being sent, which is the second part on each of those flashcard things. Very clear in the photosynthesis overview what the answers to those questions are. It will be a little bit more difficult in cell respiration. We good? Questions? Okay. Here we go. Light independent reactions. Give it a second. ATP and NADPH coming from the light dependent reactions provide the energy to power the phases of the light independent reactions. In brief, those phases are this. CO2 comes in. A molecule called ribulose bisphosphate, which is, you're welcome to abbreviate as RUBP, grabs carbon dioxide from the air. That's the molecule that fixes the carbon. The carbon dioxide gets rearranged with a bunch of other carbons from previously in the cycle into various carbon-containing molecules. Some of those molecules are made into glucose. The rest are recycled to grab more carbon dioxide. You can draw it now. That's the one you're going to draw. Don't miss the words in green, which are regeneration, carbon fixation, and reduction. So now, yeah, sorry, Lauren.
Why is CO2 in a bubble?
Why is CO2 in a bubble? Because it's a gas. It's the best way I could show that it's a gas coming in from the atmosphere. Limited to the tools that Microsoft gave me. Okay, so now I'm going to show you a little more detailed version that shows that this really is essentially a carbon rearrangement game. Each of these molecules is carbon-based and is made of a certain number of carbons. And by following those numbers of carbons, you can sort of see what's really going on. You don't have to memorize what I'm about to show you. You do need to know a couple of details. Don't draw it. I will give it to you on paper tomorrow. But here we have it divided into those three phases that I gave you in green up here: regeneration, carbon fixation, and reduction. Regeneration, carbon fixation, reduction. And I've got the carbons and the phosphates kind of in little circles here so you can keep track of them. And the little numbers here are like coefficients. They tell you how many in the real deal, in actual Calvin cycle, this is how many of those molecules are involved. So what we have grabbing 6 carbon dioxides from the atmosphere is 6 of these 5 carbon molecules called RUBP, ribulose bisphosphate, okay? And those have had phosphates stuck on either end of them to give them the energy to do what they're about to do, which is to grab the CO2 that's coming in from the atmosphere. With me so far? Those 6 RUBPs and the 6 carbon dioxides get stuck together. And what you end up with is six carbon molecules. But immediately, those six carbon molecules get split into 12 3-carbon molecules. They look like this. Okay, 3 carbon molecules, each one with a phosphate, because the phosphate was on either end, right? So if you put another carbon here and then split them all in 2, you now have 12, twice as many of the 3 carbon molecules with the 1 phosphate on. So that's the carbon fixation phase, is RUBP grabbing CO2 from the atmosphere. Then ATP and NADPH do their work, which is the ATPs stick a phosphate onto the other side, right? So now it's a double phosphate molecule, giving it more energy. And then the NADPH does its thing by what we call reducing. Okay, reducing the 12 to 12 without the phosphate and kind of rearranging it a little more. And at that point, during this reduction phase, is when some of these 3 carbon molecules will then get stuck together to make glucose. So this is where glucose comes up, during the reduction phase. Notice that the vast majority of molecules we're dealing with here are 3 carbon molecules. Most of the action here happens with these 3 carbon molecules. 2 of those 12 made a glucose. 10 of them come back around. Lose their phosphate, get more phosphate, and become RUBP. All of this movement of phosphate and reduction stuff, that's not for us this year. Okay, we don't care about that as much as you will if you take AP Bio. What you need to know is the 3 phases: carbon fixation, reduction, and regeneration, and the main event of each. The main event of carbon fixation is grabbing CO2. The main event of reduction is making glucose. And the main event of regeneration is making the grabber again. With me? Grabbing carbon dioxide, making glucose, making the CO2 grabber again, out of the stuff that you made glucose with, what's left over that you didn't use. Okay. Questions? Very carefully. I don't know. I don't have a good detailed answer for you, so don't worry about it.
Where does the oxygen go after it takes the carbon? Does it just take the carbon?
No, the oxygen winds up in there too. We're just only tracking the carbons. Good question. Yeah, but yeah, the RUBP has oxygens on it, just like the glucose does, right? It's got all these OHs on it. Yeah, they're not gone here. They're just we're not worrying about them. We're playing a carbon tracking game pretty much.
The Calvin cycle, is it like just a name for all independent reactions? Or is it just this cycle?
This is the light independent reactions. Calvin cycle is a term for the light independent reactions. Those are interchangeable terms, and this is all of that. This is it. There's no more.
The NADPH provides, you said it drives hydrogen or glucose to make?
It's more like it provides electrons. So it's coming in and giving up that high energy electron. And when we say reduction, if you're familiar with chemistry, you know that reduction and oxidation have to do with gaining and losing electrons. When something is reduced, that means it gains electrons. And so that's why we call this reduction. This thing is donating electrons to provide energy for this thing to rearrange and do stuff. Again, not a detail you necessarily, I mean, you need to know this is carrying electrons and giving them up. But as far as knowing exactly what reduction is, you're okay. This is one of those things, what makes this hard is that I can't go all the way into the total detail, because we don't, that's too much for us. You know, you'll get more in AP Bio, and even more if you become a botanist, right? You'll understand this incredibly well. Here we have to kind of take the fillet, right? We have to kind of just skim off the top and get as much understanding as we can. And that's what we're trying to do. Okay, that is photosynthesis for us. Tomorrow, we'll do some kind of, I don't know, some cleanup. But at this point, you've got what you need to finish the top 2 flashcards, right? Which are the light dependent and light independent reactions. Tomorrow, that's one of the random things we're gonna do is get some closure with our eggs, which we kind of left hanging there. The other thing I want to give you is just kind of a fun thing related to last chapter. I'll give it to you first and see what you can make of it. One of the things being a parent teaches you is that it's really hard to explain things when your vocabulary is limited. The first time that an 8-year-old says, "What are we made of?" and you have to use words that an 8-year-old understands to explain like cells. Not easy. So with this person who wrote the book that this page is from, who actually is one of my favorite webcomic people, a webcomic called XKCD if you're interested. I don't remember that problem. Anyway, what this person decided to do was explain as many scientific models and concepts as he could using only the 1,000 most commonly used words in the English language, which he discovered was very hard when he first did it. The first thing he tackled was the Saturn V rocket that took space shuttles into space, and it ends up being pretty funny the way things that are simply explained can be, like calling cells tiny bags of water, right? But I decided we should probably make some kind of exercise out of it. So what I've done is numbered the cell parts that he's explaining, and your job is going to be to figure out which cell parts he's talking about. So on the back of this sheet, I'll just have you number 1 through 11. Let's see if you can figure it out. Besides being up on your independent and dependent reactions, that's your homework. See if you can figure out those cell parts.